In 2000, voxel-based morphometry was introduced, and its application to the white matter has improved our knowledge of various mental diseases, including multiple sclerosis, autism, and Alzheimer's disease. 7 years later, it was shown that the use of the full tensor in registration further improves our knowledge of white matter morphometric differences. Furthermore, DTI also enables the analysis of white matter microstructure. The diffusion tensor model is not a good model when there are multiple fascicles crossing in one voxel. By contrast, multifascicle models offer a separate model for each fascicle, solving this crossing fibers problem. But then one question naturally arises. How can we leverage multifascicle models for population studies? When we have a population of subjects to analyze, we first want to align them, and once they are aligned, we can build an atlas, which is then at the basis of the analysis. We therefore need a way to compute linear combinations and a similarity metric for multifascicle models. These will enable interpolation, atlas construction, tractography, and registration in the space of multifascicle models. Let's first focus on the linear combinations. Linear combinations are required for interpolation, where the value at a non-grid location is estimated as a weighted combination of neighbors on the grid. When it comes to atlas construction, we typically need to average the values of all aligned images. This averaging also requires the computation of a linear combination of multifascicle models. So an easy way to compute these linear combinations would be to compute the weighted sum of the corresponding Gaussian mixture to yield a complete mixture. This complete mixture, however, has a lot more components than the initial images, making the result more complex than the input images. We therefore want to simplify this complete mixture to obtain an image which contains as many components as the initial images. Going from the complete mixture to the simplified mixture is an optimization problem in which we want to minimize some discrepancy between the two. As a measure of discrepancy, let us choose the cumulative differential entropy. We can optimize the parameters of the simplified mixture in an EM scheme. Since linear combinations of mixtures needs to be performed in millions of voxels, this process would be perfectly useless if it was too long. Thanks to a paper published by Davis and Hillon in 2007, we can however solve both the E step and the M step in closed form. This makes the optimization very efficient. Now that we have a method to compute linear combinations of multifascicle models, all we need is a similarity metric to perform registration. When defining a similarity metric, we need to know what differs and what's similar between the images to register. A good similarity metric varies with what is similar and is invariant with respect to what differs. If we look at diffusion images of two different subjects, we realize that diffusivities at a common anatomical landmark differ. A good similarity metric for diffusion images should therefore be invariant with respect to absolute differences in diffusivities. To achieve this invariance, let us start with the normalized correlation coefficient, which is invariant under linear transformations of the voxel intensities. Let us first generalize the concept of mean, which can be understood as the projection of an image block R onto a constant block T. Keeping T as any constant block, we obtain a new correlation coefficient which is invariant under any linear combination of T and the initial block R. Now, let's take the generalization one step further by replacing the scalar product by any scalar mapping. This yields a very generalized correlation coefficient. However, not all scalar mappings guarantee that the similarity metric preserves some invariance properties of the correlation coefficient. To preserve the invariance property, the scalar mapping should respect four conditions. A good candidate scalar mapping for multifascicle images is based on the log Euclidean scalar product of tensors. The resulting correlation coefficient is invariant under linear transformations of the diffusivities in the log domain, which is precisely what our cross-subject observation of diffusivities required. Alright, so we now have a method to linearly combine multifascicle models and a similarity metric to register them. But what have we really gained? To answer this question, let's first build a multifascicle atlas based on the developed registration method. Using this atlas, we are now in a position to perform population studies. As an illustration, we perform a population study of tuberous sclerosis complex, a disease which affects the entire white matter. Let's first look at the log Jacobian of the deformation fields, which measures local volume differences. What we observe is that multifascicle models reveal more morphometric differences than DTI. Let's now compare them in terms of microstructural differences of the white matter in the arcuate fasciculus, a set of pathways involved in language. Again, what we observe is that multifascicle models reveal more differences than DTI. As a conclusion, registering and analyzing multifascicle models has been made possible by the introduction of Gaussian mixture simplification and a generalized correlation coefficient. The use of multifascicle models in the white matter population studies is promising, and we believe it has a long way to go. Thank you.